this lecture, I have just derived the first energy equation and also applied and showed you two very important illustrations of the energy equation. Now let me derive the second energy equation. From the combined two laws of thermodynamics, we have du is equal to TdS minus PdV. Let me divide this equation by dP. I would then get du by dP is equal to TdS by dP minus P dV by dP, where u, s and v are taken to be functions of T and P, and mind you, temperature and pressure are independent variables. Thus we have du is equal to Cv dt plus A by V square into dV. To get u, I will take the integral of both sides and I get now u is equal to integral Cv dt minus A by V plus constant. It follows therefore that the internal energy of a van der Waals gas increases as the volume increases, while the temperature remains a constant, that is an isothermal process. As du is equal to TdS minus PdV, we substitute for TdS from the relation TdS is equal to Cv dt plus T delta P by delta T at constant volume dV. We would then get du is equal to Cv dt plus T delta P by delta T at constant volume dV minus PdV. Rearranging the terms, I would get Cv dt plus T delta P by delta T at constant volume minus P into dV. The energy equation gives delta U by delta V at constant T is equal to T times delta P by delta T at constant volume minus P. Call this equation 3. Substituting 1 and 2 in 3, I get delta U by delta V at constant temperature is equal to RT by V minus B minus RT by V minus B plus A by V square. So again you can see RT by V minus B gets cancelled and I am left with A by V square. So we get T delta P by delta TV minus B is equal to A by V square. So this means that we have derived the energy equations and we have now seen how these energy equations can be applied and to the TdS equations and how we can show the various illustrations. So next let me just come to the very important energy equations. Just let me get to the slide. So now we come to the third application, which is the heat capacity equations. Let me find out the expression for difference in the molar specific heat capacities. The first and the second TdS equations are given by TdS is equal to Cv dt plus T times delta P by delta T at constant volume into dV. So we get TdS is equal to now Cp dt minus T delta V by delta T at constant pressure into dP. If we equate the above equations, because we see the left hand side of both the equations has TdS, so we can equate them. Left hand side is equal. This means that the right hand side also has to be equal. So we get Cp dt minus T times delta V by delta T at constant pressure into dP is equal to Cv dt plus T delta P by delta T at constant volume into dV. Rearranging the terms, we get Cp dt minus Cv dt is equal to T times delta V by delta T at constant pressure dP plus T delta P by delta T at constant volume dV. Or we get Cp minus Cv into dt is equal to T delta V by delta T at constant pressure dP plus T delta P by delta T at constant volume into dV. Or dt can be written as, if I take Cp minus Cv to the right hand side, I get T times delta P by delta T at constant volume divided by Cp minus Cv into dV plus T into delta V by delta T at constant pressure divided by Cp minus Cv into dP. Now, because dt is a perfect differential, we have dt is equal to delta T by delta V at constant pressure into dV plus delta T by delta P at constant volume into dP. If we equate the coefficients of dP and dV of the equations 3 and 4, we get delta T by delta V at constant pressure is equal to T delta P by delta T at constant V divided by Cp minus Cv. This is a very important equation. So, if we rearrange the terms in this equation, we get Cp minus Cv is equal to T times delta P by delta T at constant volume into delta V by delta T at constant pressure as shown in equation 7. This is an extremely important equation and has many practical applications and can be used in various mathematical numerical problems. Now, to put 7th in some other alternative form, let us consider pressure as a function of temperature and volume. Since dP is a perfect differential, so dP can be written as delta P by delta V at constant temperature dV plus delta P by delta T at constant volume dt. If the change takes place at constant pressure, we have dP is equal to 0. Then we can write 0 is equal to delta P by delta V at constant temperature dV plus delta P by delta T at constant volume dt. Transposing one term to the left hand side, we get delta P by delta T at constant volume into dt is equal to minus of delta P by delta V at constant temperature dV. Or delta P by delta T at constant volume can be written as minus of delta P by delta Vt into delta V by delta T at constant pressure. Call this equation 8th. So, what have we done in equation 8th? We have transposed dt of the preceding equation to the right hand side. Now, let me substitute 8th in 7th. We get Cp minus Cv is equal to minus T delta V by delta P square into delta P by delta V at constant temperature. The above equation is very important and has many physical significances. First, since delta P by delta Vt is always negative for all known substances. Why is it negative? Because increase in pressure always results in the decrease of volume. And delta V by delta Tp must be positive because it is occurring in the square. Therefore, Cp minus Cv can never be negative or Cp can never be less than Cv. Cp is always greater than Cv. When the temperature approaches 0, Cp has to approach Cv, or we can say that at absolute 0, the two heat capacities are equal. This we can see from the third law of thermodynamics also. Further, when delta V by delta T at constant pressure is 0, we get Cp is equal to Cv. For a perfect gas, Pv is equal to RT, and so we have delta P by delta T at constant volume is equal to R by V, and delta V by delta T at constant pressure is equal to R by P. From equation 7th, we get Cp minus Cv is equal to T times delta P by delta T at constant volume into delta V by delta T at constant pressure. If we substitute the above conditions in equation 7th, we will get Cp minus Cv is equal to T into R by V into R by P. Just simplifying this equation, we get R square T by Pv. Pv is nothing but RT, so we get R square T by RT, or simply R. So we have arrived and we have derived a very important relation. Cp minus Cv is equal to R. This is called the Mayer's equation, and it holds true for ideal gases. Next, let us calculate and derive the ratio of the specific heat capacities. We know that specific heat capacities are Cp and Cv. So what do we have to find out? We have to find out that Cp by Cv is equal to gamma. The two TdS equations can be written as TdS is equal to Cv dt plus T times delta P by delta T at constant volume into dV, and TdS is equal to Cp dt minus T times delta V by delta T at constant pressure into dP. Let me call these two equations 1 and 2 respectively. If entropy is constant, the two equations would become Cv dt is equal to minus T delta P by delta T V dV, and Cp dt is equal to T times delta V by delta T at constant pressure into dP. Call these equations 3 and 4. If we divide both the equations, we get Cp by Cv is equal to minus of delta V by delta T at constant pressure divided by delta P by delta T at constant volume into delta P by delta V at constant entropy. The quantity in the square bracket can be seen that it is equal to minus delta V by delta P at constant temperature. Thus, what do we get? We get Cp by Cv is equal to delta P by delta V at constant S by delta P by delta V at constant T. The adiabatic compressibility is defined as beta S. Beta means compressibility, adiabatic means the subscript S. It is defined as minus 1 by V delta V by delta P at constant S. Likewise, the isothermal compressibility can be defined as beta T is equal to minus 1 by V delta V by delta P at constant temperature. So, we therefore have Cp by Cv is equal to beta S by beta T, which is equal to gamma. Now let me discuss the fourth application of the Maxwell relation, which is very, very important. It pertains to the derivation of the Clausius-Clapeyron equation. What is the Clausius-Clapeyron equation? It is an equation which shows how melting point or the boiling point vary with pressure. That is, we have to find out a relation in which we find out the differential dP by dt. Using Maxwell's thermodynamical relations, we can deduce the Clausius-Clapeyron equation. From the Maxwell's second relation, we have delta S by delta V at constant temperature is equal to delta P by delta T at constant volume. Here again you will appreciate that we are getting a positive sign because S, P, T and V are occurring in the clockwise direction. Multiplying both sides by T, we have T times delta S by delta V at constant T is equal to T times delta P by delta T at constant volume. The second law says that TdS is equal to delta Q. So we get delta Q by delta V at constant temperature is equal to T times delta P by delta T at constant volume. Now what is the quantity on the left hand side? It is the heat absorbed or liberated per unit change in volume at constant temperature. For constant temperature, the heat energy absorbed or liberated will bring a change in the volume of the substance from V1 to V2 such that instead of delta V we can write V2 minus V1. Now because the temperature remains a constant, the heat absorbed is used in changing the state of the body from the solid to liquid or from liquid to gas, which is defined as the latent heat and denoted by symbol capital L. So we have delta Q is equal to mL. Thus we have mL divided by V2 minus V1 is equal to T times delta P by delta T at constant volume. Simplifying this, we get delta P by delta T is equal to L by T. Now we get V2 by M and minus V1 by M. Here both the volumes are divided by mass. Whenever we divide a quantity by mass, we can define that quantity as the specific quantity. So V2 by M can be written as small v2, which is the specific volume. V1 by M can be written as small v1, where v1 also denotes the specific volume. P refers to the saturation vapor pressure, L is the latent heat, T the temperature, V1 and V2 are the specific volumes of the liquid and vapor respectively. This equation is known as the Clausius-Clapeyron equation. It is one of the most important formulae in thermodynamics and gives the rate at which the vapor pressure must change with temperature for the two phases to coexist in equilibrium. Now what happens during a change of state? During a change of state, either from solid to liquid or liquid to vapor, the temperature remains a constant as long as the change is taking place. This temperature, which is either the melting point or the boiling point, depends upon the pressure and is characteristic of the substance. Now mind you, we can also obtain the Clausius-Clapeyron equation from the equality of Gibbs free energy in two coexisting phases also, and in my subsequent lectures I would be doing this also in these lecture series. We know the specific volume of vapor has to be greater than the specific volume of liquid. This would mean that dP by dt saturated will be positive, implying that increase in pressure raises the boiling point and vice versa. This is very important, and we see this happening in our everyday life also. How? This explains why vegetables cook faster in a pressure cooker, because what is happening in a pressure cooker? The pressure is increasing. Because of the increase in pressure, the boiling point increases. When I say the boiling point is increasing, it means that more heat will be provided to the vegetable in the cooker, and therefore they get cooked faster. This also explains why it is difficult to cook food at high altitudes than at sea level. Because at high altitudes the pressure is less, so boiling point is less. It means less heat will be given to the food which is kept for cooking, and therefore it will take a longer time to cool. So here we can see that the Clausius-Clapeyron equation applies to all first order phase changes in which entropy and volume are discontinuous at the transition temperature. More on this will be discussed in my subsequent lecture on the Gibbs potential and how to derive the Clausius-Clapeyron equation and the Ehrenfest equations. Now I will show you the phase diagrams for carbon dioxide and water. These curves represent a unique relationship which must hold for the two phases to coexist. Note that the three curves intersect at one point. This point is called the triple point. This figure is showing the phase diagram for CO2. You can see on the left hand side we have the solid CO2, on the right hand side, upper right hand side we have the liquid CO2, and on the bottom we have the gaseous CO2. All the three are coexisting at one point, which is called the triple point. The pressure at the triple point is 510.2 kilopascals, and the temperature at the triple point is 216.8 Kelvin. The point on the PT diagram where all the three phases coexist is known as the triple point. For CO2, Tp is equal to minus 56.6 degrees Celsius or 216.8 Kelvin, and PTV is equal to 5.11 atmosphere. Whereas for water, as I will just show, the triple point is defined by temperature Tp is equal to 0.0075 degrees Celsius or 273 Kelvin, and PTP is equal to 4.58 atmospheres. So this is the phase diagram for water. You will appreciate one thing, that the line which separates solid to liquid has a negative slope here, which is in contrast to the phase diagram for carbon dioxide. The slope of the solid liquid curve is positive for water. This means that most substances will expand on melting and dP/dt is going to be positive. So the melting point of such materials will increase when the pressure is raised. On the other hand, the solid liquid curve for water has a negative slope, implying that the water expands on freezing and its melting point decreases when pressure increases. Note that water is an exception at the triple point. It passes from vapor to solid to liquid phase when the pressure is increased. Here I am showing the phase diagrams for carbon dioxide and water side by side. You can see that for water we have a negative slope in the solid liquid interface, whereas for the carbon dioxide we have a positive slope in the solid-liquid interface. You can also appreciate the difference in the triple points, in the values of the triple points pertaining to temperature and the pressure in both the cases. So this is as far as the fourth application. Now let me move on to the fifth application. What would be the effect of pressure on the substances that expand or contract on heating? From the Maxwell's fourth relation, we have delta S by delta P at constant temperature is equal to minus of delta V by delta T at constant pressure. If we multiply both sides by T and use the definition for alpha, we get delta Q by delta P at constant temperature is equal to minus TV alpha. So what we get? We get delta Q by delta P at constant temperature is negative. Also, since dP is positive, in case of dQ is negative, that is when heat is taken away from the substance, the temperature remains a constant. Thus, a substance which expands on heating, when we compress it, heat is produced. And cooling is produced when we compress a substance which contracts on heating. Mind you, water below 4 degrees cools by adiabatic compression, while above 4 degrees centigrade, it will cool by adiabatic expansion. So this was some of the applications of Maxwell's relation. In my subsequent lectures also, I will be devoting time and discussing a few more applications, and also I will be discussing some very important problems pertaining to Maxwell's relations. I hope you have understood today's lecture and will be present in the next lecture as well. So, see you. Thank you.